Let us start our today's session. So give me a moment. Yeah. Show that the tangent planes at the extremities of any diameter of an ellipsoid are parallel. So this was the question. Please take a note of that, then inform. So is it noted? Right. So let us consider the ellipsoid here. And by default, the center is nothing but origin. And the equation of ellipsoid is x square by a square plus y square by b square plus z square by c square equal to 1. So in the problem, what we are doing, we are calculating the tangent planes at the extremities of a diameter. I think you know what is meant by the diameter and the extremity. Say extremity is nothing but the end of the diameter, right? So let us say if this is the diameter you have considered, this is one end point and this is the other end point. And what he is saying here, if you consider tangent planes at this point and here also, then these tangent planes are parallel. That is he is mentioning, right? That we have to prove actually. Is the question part clear? Say. Right. Now, if you consider the line passing through the center and perpendicular to the tangent plane, so it is nothing but x by L is equal to y by m is equal to z by n. You can take the parametric form R. So it is nothing but x equal to LR, y equal to mr, z is equal to nr. So for different values of r, we will get different values, I mean different point on this line. So at this position, for a particular value of r, you will get the point, and here also you will get. Since you are taking the end points of it, if one point is negative and other one will be positive, because you are taking the opposite ends. And the center is nothing but the origin here for the ellipsoid. So since the point lies on the ellipsoid, it will satisfy the equation of the ellipsoid. So if you substitute the values there, you will get L square R square by A square plus m square R square by B square plus n square R square by C square is equal to 1. So which gives that this is the value. Clear? Right. Now let us take the reciprocal and let us consider the value of r. So this implies that r equal to plus or minus 1 by square root of L square by A square plus M square by B square plus N square by C square. Agreed? The value. Now, so let us take that this expression, let us give a name for it, is equal to K. This part I am taking it as the value K. Now, if you want to consider the tangent plane at this point for the ellipsoid, let us write it now. I think you will know the formula for the tangent plane. So whenever you have considered the ellipsoid equation, we will write the tangent plane as x(x1) by a square plus y(y1) by b square plus z(z1) by c square is equal to 1. So here x1, y1, z1 is nothing but the point at which we are considering the tangent plane. Since we are considering the tangent plane at this point, and understand that here we have taken r is equal to some value plus or minus k. So at what point we have to take the tangent plane? LK, MK and NK. So this is one point, and the other end point is nothing but minus LK, minus MK and minus NK. So at these points we are considering the respective tangent planes. So what happens here? One tangent plane is nothing but xLK by a square plus ylk by b square, ymk plus znk by c square is equal to 1, which gives that accepted the value of the tangent plane. So I have taken one endpoint LK, MK and NK. If you take the other endpoint, the other tangent plane, we will get it as Lx by a square plus My by b square plus Nz by c square is equal to minus 1 by k. So this is one tangent plane at one endpoint, and this is another tangent plane at the other endpoint. Please check on that. You confirm your view. Do you agree or not? So if you observe the tangent planes here, see the respective coefficients of x, y and z are same, only they are differing by a constant. In both the plane equations, coefficient of x, y and z are same, only constant is different. So such planes we call them as parallel planes. Agreed? Since we have considered the tangent planes at the end points of the diameter, so whatever the tangent planes we consider at the extremities of any diameter, they are nothing but parallel planes. So here the proof completes. Right? Then I will take the next model. Please take a note of that, then inform. The next problem is prove that the equation to the two tangent planes to the conicoid which pass through the line This is the question. So just take a note of that, then you inform. Then we discuss with the approach. Even though the problem seems to be somewhat lengthy, but it is very easy to calculate. The simple problem it is. After noting, you please tell. So just look at the question tag that here for the conicoid we are considering a tangent plane. However, you are going to get the two tangent planes. You forget about that. We are calculating a tangent plane to the conicoid, and the tangent plane has a property that it passes through the line. So how the line is formed here? Intersection of two planes. So if you have a small visualization, let us say this is our conicoid. For this conicoid, we are calculating a tangent plane where it contains a line on it. This is the visualization. So on seeing this, what is the formula we have to use to calculate the plane equation here? Are you getting the idea? I want to calculate a plane which is containing a line, and the line is given in unsymmetric form. So what formula generally we use? I will give one more hint that suppose pi 1 and pi 2 are two planes which are intersecting planes. So we get a line here. So what is the formula we use to calculate a plane containing the line? So pi 1 plus lambda pi 2 equal to 0. So here also we apply the same procedure. So you can use lambda, mu, k, anything. The parameter you can take that. So here, if you apply the same thing, for the given planes. So you have Lx plus My plus Nz minus P plus K into L dash X plus M dash Y plus N dash Z minus P dash equal to 0. So what is the form I have written? I have written that U plus K into U dash equal to 0. This is the value I have written here. Now, if you take the terms as common there, you get that L plus K L dash of X, M plus K M dash of Y, N plus K N dash of Z minus P minus Kp dash equal to 0. In other words, minus of P plus Kp dash equal to 0. So you can modify that. You can take the constant on the right hand side so that you will have this value is nothing but P plus Kp dash. You can write like that. So this is the required plane which is passing through the given line. Now the question is, what is the condition we have to check with the conicoid if this is the tangent plane of it? Can you remember the condition of tangency when a plane touches a conicoid? So the condition is nothing but it is of the form L square by A plus M square by B plus N square by C is equal to P square. Can you remember that? So let us use the same condition here where P is nothing but the distance value in the plane, the constant value you take. Element values are nothing but coefficients of x, y, z in the plane equation. ABC values are taken in the conicoid part. So I will make space here. So what happens? I am going to use the condition of tangency there. So you have L plus KL dash by A, this part whole square plus agree all of you? By default, P is nothing but the distance from origin to plane, because in the problem it is mentioned that Lx plus My plus Nz equal to P. So by default, the plane equation is considered in the normal form, where it is given like that. Lmn are the DCs, P is nothing but the distance. So there is no need to give that specifically where P stands for the distance. Right. Now you can expand the numerator values using A plus B whole square, and you can take in the terms as common. So I will write the part that you will get K square into the value L dash square by A plus M dash square by B plus N dash square by C minus P dash square, and the other terms will come as so if you expand the numerator with A plus B whole square, and if you take the terms as common, this is the result we will get. Please observe the pattern, how it is written. If you agree with this, I will take the next step. So, actually, from the problem itself, so if you expand with a plus b whole square, you will get 2k, right? In the numerator. I hope you are applying a plus b whole square. So L square plus 2k L dash plus L dash square, isn't it? Right. So from the problem, it is given that this is the answer. Actually, here we need to complete the solution. This is the solution of the problem. And as per the problem data, we have to bring that the required plane equation will be of this form. So, if you compare these two, if you take a suitable value in place of k, you will get the required solution. Because you can observe the part k square, u square, these parts you can observe that. So for that, what is the value I need to substitute in place of k? Because initially I have taken that u plus k u dash equal to 0. From this I can write k is equal to minus u by u dash. Say. So substituting k is equal to minus u by u dash, in this position we will get the required solution. That's it. If the solution part is not given in the problem, here we conclude that this is the solution of the problem. Since it is given that, we have to find the value of k. So the k value is taken from the equation what you have written. So this is the total solution of the problem. Please check on that. So the next problem is tangent planes are drawn to so please take a note of that. Now, can you elaborate the idea? What we need to do actually here? Any guesses for anybody? Right. So if you observe that through the point alpha, beta, gamma, we have considered the tangent planes, right? So whenever a point is given, if you want to write the tangent plane equation, it will be generally, we will write like this. Say the equation of the tangent plane, I mean the equation of the plane, right? Since the plane passes through this point, alpha, beta, gamma, if you substitute alpha, beta, gamma here, p value is nothing but L alpha m beta and n gamma. Accepted? Right. So here the value of P is nothing but L alpha, m beta, n gamma. You can also remember the concept in the other way around. So you can use the formula that L into x minus alpha plus m into y minus beta plus n into z minus gamma equal to 0. This is the plane equation. That also you can use, the same value you will get, no change at all. Okay. Now, as we have taken the plane equation, since it is the tangent plane to the conicoid, the given conicoid, we will apply the condition of the tangency. So, from the condition of tangency, you can simply write it as a square L square plus b square m square plus c square n square is equal to the distance whole square. Agree, all of you? Right. Now you have done with half part of the problem. Now let us read the second line of the problem. You are writing perpendiculars from center to the planes. So what is the conicoid center here? 0, 0, 0. And from 0, 0, 0 to the plane, you are writing the perpendicular, in other words, the normal equation. So what could be the normal equation? It is nothing but x by L is equal to y by m is equal to z by n. Say, yes or no? I have written a normal equation from origin to the plane. So here Lmn values, you take the proportional values. L is nothing but x, m is nothing but y, n is nothing but z. So here you can write it as the equation a square x square plus b square y square plus c square z square is equals to gamma z whole square. You please take a note of that. Right. So at this position, we have arrived with the solution. I just want to do a small modification in the problem. Same question will be asked on two things. One, question based on ellipsoid. Two, question based on conicoid. So here, whenever you take the question based on ellipsoid, you will get a different answer. If the question is based on conicoid, you will get a different answer. Right? I think I have written the condition correctly, that condition of tangency. Could you check on that? Is the condition what we have written for the tangency, is it correct? The condition of tangency? Please check once. The condition of tangency what we have written? there are two conditions we are going to write. One condition is P square is equal to L square by A plus M square by B plus N square by C. Another condition is different. So here, for the condition of tangency, to get the answer, I am using the part that so substituting x, y, z here, you will get the required answer. Right. So, as per the question tag, I am using the respective condition. Please observe that. To get the answer, I am using the required condition. The question is very simple. We just have to take only two steps. Step 1, we have to write the plane equation. Step 2, we will write the condition of tangency. In step 3, if you substitute the proportional values of element, you will get the required answer. That's it. Only 3 steps for the solution. Please understand that. So there are two things. So if the question is given on conicoid, this is the condition of tangency, right? If the question is given on ellipsoid, the previous thing we will consider. Agreed all? Please check with the condition of tangency from your notes. We have two conditions for checking tangency. So if the same question is framed on this, the procedure is similar. The answer is just like 3 steps. We will write the plane equation, step 1. Step 2, we will verify the condition of tangency. Step 3, writing normal equation, we will substitute element values, we will get the solution. That's it. So you take a note of that. I will go to the next model. So earlier I have taken the condition of ellipsoid apart from conicoid. So last step, in this condition of tangency, if you substitute x, y, z in place of element, we will get the answer. That's it. Only 3 steps. Did you observe? The answer is given in the problem itself. Okay? The answer is given in the problem itself, right? Because it is given that show that the perpendiculars from center of the conicoid to these planes generate this equation, isn't it? The answer itself is given in the problem. And if you are interested, we can discuss one more problem, that on observing this equation, what we can talk about the locus of this equation. The surface gives what? Is it a sphere, a cylinder, or conicoid, or cone, anything? What it is? This locus, if you call. Can you tell? The resultant equation, the locus gives what? It is nothing but a cone, because you are taking the value from origin, so it will not contain the constant term, that is one. And if you expand the left side value, it is nothing but a homogeneous equation of second degree in the variables x, y, z. So we have studied that whenever you take a homogeneous equation based on origin, it always gives a cone equation, and the vertex of the cone is nothing but origin. We have given one statement earlier. So if the question further asked that, so talk about or comment about the locus, we say that the locus is nothing but a cone. So you take a note of that. The locus is nothing but a cone. So be careful while writing the condition of tangency. If you have taken the wrong condition of tangency, then you will be wrong in getting the idea. Yeah. So the current problem will be interesting for you. Obtain the tangent planes for the ellipsoid x square by a square plus y square by b square plus z square by c square equal to 1, which are parallel to Lx plus My plus Nz equal to 0. If 2r is the distance between them, show that a line through origin and perpendicular to the planes lies on so take a note of this one also. This also will be interesting for you, I hope. It is also very simple and easy problem. So for the ellipsoid, we are writing the tangent planes. And what is the property of the tangent plane? It is parallel to this plane. So observe that this plane is passing through the origin. So whenever you write the plane equation which is parallel to this one, it is nothing but Lx plus My plus Nz is equal to some constant, say it is nothing but P. Accepted? Because we are going to write the parallel plane equation for this first. And we have a specific value for P also. From the definition of tangency, P is nothing but plus or minus square root of a square L square plus b square m square plus c square n square. Because whenever you say that the plane touches the ellipsoid, the condition of tangency, as I have stated earlier, a square L square plus b square m square plus c square n square is equal to p square. So from this, the value of P is nothing but plus or minus this value. Agreed? So by taking plus and negative signs, we will get two tangent planes. So what are those tangent planes? One tangent plane is Lx plus My plus Nz equal to square root of a square L square plus b square m square plus c square n square. This is one tangent plane. The other tangent plane is Lx plus My plus Nz is equal to minus square root of This is the second tangent plane. Please check on that. Accepted. So the first part of the problem is finished. You have calculated a tangent plane for the ellipsoid and the tangent plane is parallel to this plane. We have finished the first part of the problem. Any queries to anyone? The second part says that if the distance between the planes is 2r, then you have to bring out this kind of relation. So if you observe that these two are nothing but the parallel planes, generally while considering the tangent planes we will form the regular format because we will use the direction cosines as well as the distance, because we are, while talking in terms of distance, always we consider the tangent plane in the normal form. That's why I am writing like that. Yes, the regular, that also I agree. Even if you take the other one, so you are going to write it as xx1 by a square plus yy1 by b square plus zz1 by c square is equal to 1. If you take that, that is the tangent plane, and you have to modulate that it is parallel to this thing. How you are going to show that? You need to do a small modification on this, isn't it? So apart from, if you are not interested with the symbol P, let us take that the plane which is parallel to this is nothing but Lx plus My plus Nz is equal to K. That is by default you consider. For K, we will take the same answer, square root of this thing. No change at all. So don't understand that I have written P from the previous notations. Not like that. Whatever the plane we consider, which is parallel to this plane, is nothing but constant will vary, isn't it? That's why the constant is nothing but K. You can take P also. And for the constant which gives the distance always, so this is the standard formula for distance, because the plane you have taken is nothing but the tangent plane. Otherwise it will be any value. Since you have taken the tangent plane, the distance must be of the same kind. You cannot go beyond that as per the condition of tangency. Clear now? Why I have taken in that manner only, right? So with regard to first part, any queries for anybody in getting these two tangent planes? Fine. So what it is given in the latter part, 2r is the distance between these planes. If you observe that these two planes are nothing but parallel, so we have a standard formula for distance between parallel planes where we use that modulus of d1 minus d2 by square root of a square plus b square plus c square. This kind of formula we have used earlier for calculating the distance between the parallel planes. Can you get that? So I am going to apply the same formula between these two planes, the distance between the parallel planes. So if you write that, given that distance is 2r is equal to, taking the difference between the constants, you will have d1 minus d2, you will get modulus of 2 into square root of a square l square plus b square m square plus c square n square, total divided by square root of l square plus m square plus n square. Please check that. I applied the distance formula between the two. Accepted? Now let us take this value to the left hand side and let us do squaring on both sides. So what happens? The number 2 gets cancelled and we will have r square into L square plus m square plus n square equal to a square L square plus b square m square plus c square n square. This is the value will remain. And you can take the terms as common. So bring the values to the left hand side or right hand side you say. We will get the respective locus. And there is one more condition given in the problem that a line through origin and perpendicular to the planes lies on this equation that we have to show. However, from this very equation, we can write it as L square into a square minus r square plus m square into b square minus r square plus n square into c square minus r square equal to 0. Taking these values to the left hand side, we will get this equation. Agreed? I mean, the values. So, whenever you write a line equation from origin and perpendicular to the plane, it is nothing but normal of the plane. So, the equation is nothing but x by L is equal to y by m equal to z by n. So, taking the proportional values of Lmn, we take L is equal to x, m is equal to y, and n is equal to z. We will get this required equation. That's it. So, please check on the approach. On the whole, what we did. So, if you want to have a small refreshing idea over this, the outline of the problem. In the first step, I have written the tangent plane equation. The plane is parallel to the given plane. So I have taken that Lx plus my plus nz is equal to plus or minus p, and p stands for this value. That is part 1. Part 2, since the planes are parallel, I have calculated distance between the parallel planes using the formula. It is given that distance is 2r. So 2r is equal to distance between the parallel planes. So if you simplify this, this is the locus satisfied by Lmn. The third part, I have taken that I have to write a line equation from origin and perpendicular to the plane. Nothing but you are considering the normal of the plane. So we will take the respective values of normal. So L for x, m for y, and n for z. If you substitute, this is the required thing you will get. Okay? Please take a note of that. Are you feeling any difficulty in getting the idea of the problem? How to solve it? Any difficulty while evaluating the solution step by step from the problem statement? Because compared to the previous class session, the response is somewhat different here. Are you with me in getting the same pipeline, in getting the solution? Thank you. Thank you very much. So let us discuss the new one, which is also something interesting for you. Find the locus of foot of the perpendiculars from origin to tangent planes to the surface which cut off from its axis intercepts the sum of whose reciprocals is equal to a constant k. This is also one good problem, I think, asked in the previous questions. The current problem, what we are going to discuss, and the previous problem, what we did earlier. Both were asked in the previous papers. So first note down the question, then we discuss the approach. Yeah. So here, for the ellipsoid, you are considering the tangent planes. So in the first place, we calculate the tangent plane for the ellipsoid in the general form. So how it look like? Lx plus my plus mz is equal to square root of a square l square plus b square m square plus c square n square. So straight away I have considered the tangent plane equation from the ellipsoid itself. Now if you read the question, it is given that it makes intercepts with the axis. That is one thing. The tangent plane, what you have considered here, is making intercepts with the axis. And one more property is the sum of the reciprocals, if you consider for the intercepts, it is equal to a constant k. So you have x-intercept, y-intercept and z-intercept. You take the reciprocal of them and consider their sum. The sum is equal to the number k. Clear? That is the whole idea which is given there. So if we feel that for our understanding, let us say Lx plus my plus nz is equal to p. This is a plane, let me say. What could be the x-intercept here? For this plane, if you write the x-intercept, what is the point? P by L, right? So P by L 0, 0. All of you agree for that point? Right. So y-intercept is nothing but 0, P by M 0. And z-intercept is nothing but 0, 0, P by N. So here P is nothing but square root of this value. You got the point now? How the intercepts come? Say. So here P is nothing but square root of a square l square plus b square m square plus c square n square, the distance. So whenever you consider a plane equation of this form, the intercepts are nothing but this. And it is given one more thing. Sum of the reciprocals is equal to k. So if you take the reciprocals for it and consider the sum, it is nothing but L plus M plus N by P is equal to K as per the problem. Agreed? It is nothing but L by P plus M by P plus N by P is equal to K. Sum of the reciprocals of the intercepts is equal to K. Are you getting or not? Now, let us substitute the P value there. We got the required locus value. So, we got the thing that L plus M plus N by, I am substituting P value, A square L square plus B square M square plus C square N square is equal to K. So take this value to the right hand side and let us do squaring on both sides. So which gives that L plus M plus N whole square is equal to K square into A square L square plus B square M square plus C square N square. Now, since the last point of the problem is, if you consider the foot of the perpendicular from origin to this, so how do you write the line equation to calculate foot of the perpendicular from origin? It is nothing but x minus 0 by L, y minus 0 by M, z minus 0 by N. So in place of L, substitute x, in place of M, substitute y, in place of N, substitute z. So the required locus is nothing but x plus y plus z whole square equal to k square into a square x square plus b square y square plus c square z square. That was the thing. Find the required locus of the point. So please check on with the approach. If once you are clear with this, then I will take the next concept. Fine. If the same problem is given for the ellipsoid, let me say, or conicoid, the condition will vary a little. The new problem what I am going to take here is, so this is something really interesting for you. Just give me a moment. I will erase the problem and I consider the new one. Please write this problem. Prove that the locus of points from which three mutually perpendicular tangent planes can be drawn to touch the ellipse is the sphere x square plus y square plus z square equal to a square plus b square. So please take a note of this, then we discuss the approach. Now I ask one question, that just forget about the concept that this is the ellipse. Suppose you have taken ellipsoid, if you want to write the tangent plane equation, so it is nothing but Lx plus My plus Nz is equal to square root of agree all of you? If you want to write the tangent plane equation, it is nothing but like this. Accepted? Right. Now, ellipsoid is 3-dimensional, ellipse is 2-dimensional. So if you want to write a tangent plane for the ellipse, we have to remove the third coordinate. So it is nothing but the condition a square L square plus b square m square. Why the third one is not there? Because here z is equal to 0. So you cannot take the third one here. So this is the equation of the tangent plane which will touch the given ellipse here. Any questions to anyone? Please tell. Are you getting the idea or not? See, we are writing the plane, right? So you cannot take nz is equal to 0. Plane is 3-dimensional. If you have written Lx plus My, it will become line only, not a plane. That's why nz will remain here. Right side, the constant will come like this. The p value will come like this. Because we are considering the tangent plane, not a line. Clear now? Accepted all? Right. So, if you want to write the equation of the tangent plane, this is the specific form. This is the xyz coefficients, this is the distance. So what happens, here you are considering 3 mutually perpendicular tangent planes. So if I consider 3 planes, this is my first plane, L1x, M1y, N1z is equal to a square L square plus b square m square. What could be the second plane? L2x plus M2y plus N2z is equal to square root of a square L square plus b square m square. Here we need to take L1 square M1 square, L2 square M2 square. The third thing, if you consider L3x plus M3y plus N3z is equal to square root of a square L3 square plus b square M3 square. So these are the required 3 mutually perpendicular tangent planes which touch the ellipse. Any questions? So here we have to calculate the locus. Here locus is what? The intersection of these 3 points. So if you have eliminated the values of Lmn from these equations, you will get an equation in terms of xyz which is nothing but the required locus. So similar kind of problem we have done already. I have given a definition that director sphere. There also we have taken the similar kind of one. Can you recollect that? The word director sphere. So there what we have done, after writing 3 mutually perpendicular planes, we simply squared and add them. Here also I do the same thing. First equation you square, second equation you square, third equation you square, you add all the values. You add all LHS values, you add all RHS values. So, since you know what to do, I will write the part. So we are going to get it as x square into L1 square plus L2 square plus L3 square plus y square into M1 square plus M2 square plus M3 square plus z square into N1 square plus N2 square plus N3 square plus you will get other terms 2xy into some value, 2yz into some value plus 2xz into some value is equal to, you have the terms that having a square into value and b square into value. So a square into L1 square plus L2 square plus L3 square plus b square into M1 square plus M2 square plus M3 square. So we are squaring on both sides and we are adding all the 3 equations. Since the planes are mutually perpendicular, the DCs will satisfy the respective properties. So this value is 1, this value is 1, this value is 1, these values will become 0. Again, this is 1, this is 1. So you will get required locus, this one. X square plus y square plus z square equal to a square plus b square, which is nothing but the problem part. Clear to all? And obviously it is a sphere. The sphere is centered at the origin. Right side we are having a constant. So this locus gives the sphere equation to us. So please take a note of that, then we discuss the other concepts. I think everyone will know the properties of the DCs there. Okay? The three mutually perpendicular DCs, if you consider the properties of them. Right? So here I want to close our session here. So in the next class we are going to discuss with normal when you draw a conicoid. If you draw a normal to the conicoid, so what are the problems based on that? And if we have considered 6 normals and what is the respective intersection of that, etc., etc. So similar kind of problems we are going to do in the next session, right? So let us wind up here and we will meet in the next session. If you want to add anything, you can add, and any queries with regard to class session, you can ask. Anybody? And give me one confirmation that while doing these conicoid problems, are you feeling comfortable in getting the idea? The visualization part as well as problem solving part. Or feeling any difficulty on this? That also you can do, nothing wrong at all. We can convert ellipsoid into conicoid form and you can solve. Earlier you have done some kind of problems. I have given some problems for you as a practice, the tangent plane problems. There you can convert conicoid into ellipsoid by doing the suitable multiplication, and you can do that, nothing wrong. In the examination point of view, majority of the questions are concentrated on ellipsoid and conicoid. If you look at the previous year questions, problems are less asked on paraboloid. I will give the respective material for you. And on hyperboloid of one sheet also, we have less number of problems. And I think 2017, I hope, problems are asked on 3 conjugate semi-diameters. One concept he asked, that also we discuss at the end. Yes, majority of the questions are repeated. Let me say one thing, up to 2014 and 15, questions were repeatedly asked on the chapter of conicoid, especially the things what we are discussing now. Each and every question what we are doing in the class session is asked in the previous year papers, right from 1992, you can check on that. Now earlier from 2016 onwards, what it is done, he shifted the focus from conicoid to other chapters, cone, sphere, right line, cylinder, etc., etc. So there, initially conicoid has some lengthy answers, so students will feel difficulty. Later, he is focusing on the calculation part, how good you are in solving a problem at speedy level. So he is giving, apart from 3 questions, he is giving 4 questions. So apart from the logical thinking, he is straight away giving the questions based on a suitable formula. If you take sphere, we have formulas based on plane section, orthogonal spheres, limiting points. So straight away question is given on that. You have to solve them within the stipulated time. So solving 4 questions within the given time is somewhat difficult. If you have a thorough practice, then only you are going to solve that. Otherwise, it will be difficult for you. Isn't it? So that is the thing majorly changing in the exam point of view. And you can think questions are asked on right line and sphere in the previous exam paper. You can check on that, and plane also. So you cannot say surely that questions will definitely pose from conicoid, because lot of questions are asked on that part and questions are repeated also. I think for the next exam, you can expect questions from cone and cylinder, apart from this conicoid. I hope so. It is just guesswork. Please understand. Guesswork. As per the pattern he is doing, we can expect like that. That's it. The best part you can expect is, since the weightage is equally distributed among all the units and chapters within it, so one question from right line, one question from sphere, one question from conicoid, and one question from cylinder. So 4 questions will be given under one single Roman, either Roman 3 or Roman 4, and equally giving 50 marks for that. So what happens, even though if you skip one chapter, the rest will cover you 30 to 35 marks around it. That's a good idea. For the preparation part is considered. So if you want to give a thorough preparation, you can skip one chapter of it. Other questions you can get that from the other parts of the same content, either solid geometry or differential equations, whatever it may be. So anything else to add upon? So thanks to everyone. That's all for today's session.